Let us now discuss one of the convergence theorems in Lebesgue integration. So recall from the beginning of this course, we want to determine conditions wherein we can interchange the processes of taking the integral and limits. And the monotone convergence theorem is one of that. So suppose we have a sequence of increasing functions that are non-negative and measurable. Okay, then we can suppose this is increasing. Then the integral of the limit is the limit of the integrals. So for the proof of this theorem, so let us define the limit. So let f sub n, or let f be such that fn tends to f. Then f is measurable, being the limit of measurable functions. It is also non-negative. Okay, now from this theorem, take note that, or from this statement, take note that according to the definition, f sub n is less than or equal to f for all n. Applying monotonicity, we have this inequality by monotonicity of the Lebesgue integral for non-negative measurable functions. So taking the limit, this provides us one inequality in the convergence theorem, since take note that this is equal to f. So to prove the reverse inequality, we proceed as before. We introduce a parameter beta, which is positive and less than 1, and take phi to be a simple function. So that is, phi is a simple function, non-negative, and phi is less than or equal to f. So here we provide the alternative characterization or definition of the Lebesgue integral for non-negative measurable functions as the supremum of the Lebesgue integrals of simple functions phi less than or equal to f. So let us also define b sub n to be the set where f sub n is greater or equal to beta phi. And again, measurability of fn and phi implies that this is in a sigma. Note that first, f being greater than or equal to phi, and beta being less than 1, we have this inequality. Then we know that bn is increasing, since, okay, so if f sub n of x is greater than beta phi of x, then this is clearly, this implies that f sub n plus 1 of x is also greater than or equal to beta phi of x. So if x is in Bn, it is also in Bn plus 1, since your sequence of functions is increasing. And Bn increases to x. Since, okay, passing to the limit here, as n goes to infinity, you get the fact that this is valid for any x in your domain capital X, since beta is less than 1. And f is greater or equal to phi. Okay, also, we have the following. So these are same reasoning as before. Fn is equal to beta phi n times the characteristic function of Bn. And you can easily show this by, again, considering cases whether the point lies in Bn or not. So if it's in Bn, you can use this inequality. If it is not in Bn, then both sides are equal to 0. Now, this is clearly a non-negative simple function. And since Bn increases to x, so beta phi times the characteristic function of An increases to beta phi times the characteristic function of x, which is identically equal to 1. So based on this, we apply, let's say, the monotonicity of the Lebesgue integral on this inequality here to obtain that the beta times the integral of the simple function phi, okay, by linearity, we have this. And since phi beta phi times the characteristic function increases to this function, then taking the limit of this sequence, taking the limit of the integrals of this sequence, we have this equation here. So here we applied linearity of integral on S plus, okay. And here we have the definition of your integral or Lebesgue integral on M plus. And from here, since going back to this inequality, the third inequality, we obtain that this is less than or equal to the limit n goes to infinity of the Lebesgue integral of f sub n with respect to dimension mu. So upon taking the supremum over all simple functions phi that is less than f, so the right hand side would be beta times the integral of f d mu. And then after passing to the limit of beta to 1, this will tend to 1. and we get the reverse inequality. Okay, so again, going back to the statement of the monotone convergence theorem. So if you have an increasing sequence of non-negative measurable functions, the integral of the limit is the same as the limit of the integrals. Now, one might ask, is it possible to replace the condition of the condition that the sequence is increasing by decreasing sequence? This is not the case according to the following example. So if we define the sequence of functions f sub n from R into itself with respect to the Lebesgue measure, and f sub n is, let's say, the characteristic function of this interval n to infinity, then you know that, of course, the sets for larger n is decreasing, therefore the characteristic functions are also decreasing. And you can see that fn indeed also tends to zero function as n tends to infinity. Okay, so the integral of the limit is 0. However, take note that the integral of the f sub n's, d mu, x here is, of course, the set of real numbers, and mu is the Lebesgue measure. So this is a simple function This is basically the Lebesgue measure of this interval. This is infinite. Therefore, the limit of the Lebesgue integrals is infinite. And here you can see that these are not equal. So we cannot replace the increasing assumption by a decreasing one. And as a corollary, we can extend this to an infinite series of non-negative measurable functions. So if fn is non-negative and measurable for any positive integer n, then the integral of the sum or infinite series is the series of, or the sum of the Lebesgue integrals. Well, to prove this, one would recall that the infinite series is the limit of the partial sums. So if we denote the partial sum by, let's say, g sub n, so this is the sum of the first m terms of the sequence of functions, then it is clearly non-negative and measurable. And we know that gm increases to the infinite series. Of course, as m tends to infinity. We can now apply the monotone convergence theorem to the sequence GM, so that the integral of the limit is the limit of the integrals. So let us investigate these two. Again, we know that this one is equal to the full series. Okay. On the other hand, for the right-hand side, we apply the definition of GM and since this is a finite linear combination, we can now apply here linearity of the Lebesgue integral to deduce that this is the limit n, I should say m, of the sum of the integrals. And therefore, this is the series, the infinite sum of the Lebesgue integrals. And this should be f sub n. And that's it. So the limit, the infinite series of the, or the integral of the infinite series is the infinite series of the Lebesgue integrals. So again, you can interchange limits and integrals as long as your sequence of non-negative measurable functions is increasing. So as an application of the previous corollary, let us construct a measure out from the measure mu and a non-negative measurable function. So to start, consider a non-negative measurable function and consider nu defined on the sigma algebra. This is let us define this as follows. So nu of a is the integral of f times the characteristic function of a. The product of two non-negative measurable functions is again non-negative and measurable. So this product is in m plus. So therefore, the right-hand side is the Lebesgue integral for non-negative measurable functions. Then nu is a measure. If the measure of a is 0, then the measure of a with respect to nu is 0 as well. Here a is of course in sigma. So all null sets of mu are also null sets of this nu measure. And if G is non-negative and measurable, then this integral with respect to the new measure is the same as the integral of the product. So before we proceed with the proof, the function f is called the density. So f is called the density of nu with respect to the measure mu. And here we introduce the following notation. We also write, in this case, d nu to be f d mu. So this notation means that, or we write this, okay, if and only if we have this identity here. Or we also write in this way, the density f to be d nu d mu. So these are just annotations that can be useful later for calculations. So the idea behind this notation is the following. So nu of a is basically the integral of the characteristic function with respect to nu. Okay, since d nu is equal to f, so we have here characteristic function of a f d mu, which is the same as our definition here. Of course, once you interchange the order of the functions in the integration. Okay, so this is the motivation of our notation. So let us look at the proof of the theorem. So first, nu of a. In definition, this is when a is the empty set. By definition, this is the characteristic function of the empty set times f. Well, the characteristic function of the empty set is 0. This is 0. Now, suppose we take a pairwise disjoint sequence of elements in the sigma algebra. Okay, then nu of a, I should say nu of the union, and this is equal to the Lebesgue integral of the indicator function of the union times f with respect to the measure mu. And one can show that since the sets are pairwise disjoint, the indicator function of the union is basically the sum of the indicator functions. So here we now apply the Beppe-Levy theorem. So we can interchange the sum and the integral. But basically, the terms here is just the measure with respect to nu of an by definition. So this indeed shows that we have a measure. So nu is a measure. Now, suppose that measure of a is 0. you can easily show that the characteristic function of A times F, this is positive. If this is positive, then this is a subset of A. This follows from the fact that the characteristic function, so if this is positive, then both terms must be positive. Therefore, you need that the characteristic function must be positive. Therefore, it must be an A. So therefore, the measure where the measure of this set is 0. Hence, this product is 0 except on a null set. So we know before that the integral must be 0. But this is nothing but nu of A by definition. Okay, so that's the second property. Finally, to prove the third one, first, let us start with the case of simple functions. And consider this simple function phi with this canonical representation. And it's also non-negative. So we want to show that this equality here holds when G is equal to phi. Okay, so let's start with the left-hand side. The definition of the Lebesgue integral for simple functions implies that this is equal to this sum. Next, we apply the definition of nu to see that this is equal to the integral or the sum of the alpha sub j's times the integral of the indicator function times f d mu. Now we apply the linearity for the Lebesgue integral on non-negative measurable functions. So this is the Lebesgue integral of this linear combination times f d mu. Wherever this linear combination is phi. So this is the integral of phi f d mu. In other words, we have verified the equation in the case of non-negative simple functions. Now, for a non-negative measurable function, what we do is we take a sequence of non-negative simple functions that increases to G. And in the last lecture, we know that such a sequence exists. Now, note that the product, let's say GF, the product of two non-negative measurable functions is again non-negative and measurable. And phi n f, since f is non-negative, this increases to G times f. So we can now prove the desired equation as follows. So let's start with the left-hand side. And here, definition of, we apply the definition of integral on m plus. Okay. Since phi sub n increases to g, so this is the limit as n goes to infinity, phi n d nu. Now, we know that in the above case, the integral of the step function of a step function with respect to the measure mu is the integral with respect to the measure mu of the following function. So this is phi sub n times f. And of course, we take the limit. And with the same reasoning here, you copy that reasoning, applying the definition of the Lebesgue integral for non-negative simple non-negative measurable functions, and using this fact here, or I should say, the monotone convergence theorem. The monotone convergence theorem. Since I take note here that this is not a simple function anymore, but surely this is non-negative and measurable. Okay, so if we apply the monotone convergence theorem, the limit of the integrals is the integral of the limits. Therefore, this one converges to the Lebesgue integral of gf times d mu. Okay, so again, we can construct a new measure out from an old one and from a non-negative measurable function. And the measurable, non-negative measurable function is called the density of the new measure with respect to the old measure mu. And in fact, one can iterate this and consider, for instance, transitivity. So if we have, let's say, two non-negative measurable functions, then f d mu of g is the same as gf d mu. So the order of the densities are not relevant in this case. Well, to see this, take note that, so evaluating this on a measurable set A. So by definition, this is the Lebesgue integral over x of the characteristic function of so to let us write this first as let's say the nu. So in this case, this is equal to g d nu by definition. But then going back to the fact that d nu is equal to f d mu, and this is the same as gf. So now you take d mu, gf d mu. So this is now gf times the measure with respect to the measure A. Okay. So that's the rough proof of this equation here. So if, let's say, you can write this in an alternative form. So if you set this to be, let's say, d nu, and you set this to be d rho, for instance. So as an alternative way of writing this, so the d nu is f d mu, and d rho is equal to g d nu. So the identity say g f d mu can be written as follows. So the take note that the left hand side is d rho. G is equal to, so that's the density, so that's d rho over d nu. And f is, what is f? F is d nu over d mu. So this is f here, using the alternative definition, and we have another d mu. Okay, so you can see here roughly, algebraically or symbolically, this will cancel, so you end up with d rho. So that's way of another way of looking at this transitivity of these measures with respect to A density. So that's it for the Lebesgue integral for non-negative measurable functions. We discuss in the next lecture the Lebesgue integral for more general functions.